Well, here we are, folks, the end of the week 2 homework. Problem 5 uses the diagram that you used in problem 4. You'll notice that problem 5 is basically asking you to modify the magnitudes of vectors. So it's saying the resultant is 2 times vector A minus vector B plus 3 times vector C. Well, normally we'd be adding these vectors. This minus vector B is really equivalent to multiplying vector B by -1. So in all cases here, we're just basically modifying these vectors with coefficients that change their magnitude but not their direction. So let's think about what problem A would look like with these modifications. Well, that would mean that vector A was twice as long and in the same direction. So basically, the drawing's going to stay the same. The vector physically would be twice as long, although we don't need to extend it. I can just make a note that I'm going to strike 4 here and put 8 in its place. Vector B would be the same length, but -1 would mean that it runs in the opposite direction. So that's going to take a little bit of setting up. So vector B now runs in this direction. Its length is 7 meters. And let's try and think about an angle. We've reflected this across the origin. So that means that it's 180 degrees from this 70. Well, that would mean that it's 110 degrees from this vertical line. Well, it's 90 degrees to the horizontal line, so this included angle here is now 20 degrees, which makes sense because by the principle of similar angles, this angle here is 20 degrees, this angle here is 70 degrees when we reflect across the origin like that. So we're going to just scribble out the original vector B because it's no longer part of the problem. All of this goes away. Vector C is 3 times its original length, and again, we'll just simply multiply this number by 3 and we'll get 15 meters. Now, this might be a case where you could go back to the previous problem and just look at your answers, because if the vector is, for instance, if vector C is 3 times as long in total length, that will mean that the horizontal component of the vector is 3 times as long, as will be the vertical component. So you can't just scale the final answer that you got, but you can certainly scale the individual vectors by the new magnitude, and that will give you the new horizontal and vertical components. I don't have the old homework pulled up here, so I'll just figure these out. So for vector A, what do we know? Well, let's see. Vector A, the vertical component is opposite, and the horizontal component is adjacent. So the vertical component of vector A, or what we might say is the y component of vector A, is the opposite. We're trying to relate the opposite and the hypotenuse, so that's the sine function. Sine of 55 degrees equals what? Opposite over hypotenuse, so O over 8. And you'll notice that the only thing that is different this time is that we're multiplying by 8 instead of 4. 8 times the sine of 55 is about 6.6. Which you'll find is double the answer that we calculated last time. The horizontal component of vector A is just simply we're trying to relate the adjacent side, so cosine of 55 equals adjacent over 8. Again, 8 times the cosine of 55 degrees is going to give us the length of the horizontal component. So 55, we're in degree mode, cosine, and times 8 is about 4.6. So let's start creating our free body diagram. So we'll come down here in the lower left. And our free body diagrams here, vector A pulls downward with a distance of 6.6, and leftward with a distance of 4.6. Vector B, so let's look at vector B. Now vector B has changed. Now it's down and to the right, okay? But the math is still the same. Opposite, adjacent. So again, the horizontal component, the vertical component is going to be the sine function. So sine of 20 degrees equals opposite over 7. 7 times the sine of 20 degrees is going to be the vertical component. So 20 degrees, take the sine, times 7, about 2.4. And again, this is where you have to pay attention to direction, because now vector B is pulling downward. So now we've flipped vector B around. Vector B is pulling down with, or moves down with a distance of about 2.4 meters. The horizontal component, again, of vector B, same process. The cosine relates the opposite. The adjacent and the hypotenuse. Cosine of 20 degrees equals the adjacent side over 7. 7 times the cosine of 20 degrees is going to give us the length of the adjacent side. We'll clear this out of here. 20 degrees cosine times a unit length of 7 is about 6.6. So let's see, angle or vector B pulls to the right with a force of 6.6. And again, this 6.6 is tied to the, this other 6.6 is tied to the vertical component of vector A. Vector C. Vector C has a horizontal component and a vertical component. The vertical component is equivalent to the sine of 30 degrees equals the opposite side over 15. 15 times the sine of 30 gives us 7.5. So the vertical component, the upward vertical component of vector C is now 5.5. And let's figure out the horizontal component. So cosine of 30 degrees equals the adjacent over 15. 15 times the cosine of 30 degrees gives us 30 degrees. Take the cosine, multiply by 15. We'll call that 13 even. So 13 meters. And let's see, vector C points to the right. So 13 even to the right. Now that we have these all resolved into horizontal and vertical components, all we need to do is some simple addition and subtraction. So let's work on the vertical components first. We'll clear out of everything. So you have 5.5 upwards, and we're going to subtract from it 6.6 because that's a downward move, and then we're going to subtract from that 2.4 because that's also a downward move. And we find that the vertical result is a downward movement of 3.5. So we'll start a new free body diagram. Downward movement, 3.5. And same process for the horizontal components. Now, if you look at the horizontal components, we have two rightward moves, which we would consider positive. So it's 13 plus 6.6. And then we're going to subtract from that the leftward movement, which is 4.6. So a rightward movement of 15 meters is going to be the result. So the combination of those three moves, that 2a minus b plus 3c, is the same as moving south 3.5 meters and east 15 meters. Now we want to further resolve this into a single vector. So we will slide the vectors head to tail. Again, this is 15, this is 3.5, and we're looking to find the length and direction of this vector. Well, we'll use Pythagorean theorem, so 3.5 squared plus 15 squared equals, and I'll call it r for resultant, we'll call the length of this side r, equals r squared. Well, we want r, not r squared, so we'll take the square root of both sides. And let's do some multiplication and some exponents and some summing. So 3.5 squared plus 15 squared equals, and then we need to take the square root of that number. So we're going to raise that to the 1/2 power. And we find that the length of the resultant is about 15.4 meters. Okay, 15.4 meters. Now the question becomes, what's the direction? Well, the first thing you need to do is figure out this included angle. And so remember that the tangent of some angle, which we will call angle theta, so we'll label this as angle theta, equals the opposite over the adjacent. Well, what's opposite of angle theta? 15. And what's adjacent? 3.5. But remember that we need to use the inverse function here because we are interested in finding, we don't know angle theta, we know the ratio of the two sides. So we use the arctangent, 15 over 3.5, which will give us angle theta. So 15 divided by 3.5, and then inverse function arctangent. And we find that angle theta is about 76.9 degrees, which is a reasonable number just looking at the length of the sides. Now, think about putting this vector in the Cartesian plane. Well, if theta is 79.6, the actual heading of this vector is 90 minus 79.6. So let's do that. 90 minus 79.6. This vector is heading basically 10.4 degrees. You could think of it as south of east. Now remember the way that these vectors run, or the way these angles run, is they start at 0 pointing straight towards 3 o'clock and you go around counterclockwise. So basically the angle of this is 10.4 less than 360. So we could think about this resultant vector as being 15.4 meters long at an angle of 10.4 less than 360, which is 349.6 degrees. So you can see that when we manipulate or when we use coefficients with these vectors, we're not changing their angle, we're really changing their effective length. And remember, if you go from positive to negative, you're effectively saying, I want you to run at the same angle, but in the opposite direction. Hopefully that makes this a little bit more clear. As always, if there's anything I can do to assist your learning, please feel free to get in contact with me at the contacts listed in the course syllabus.